Hello friends, this is Anant Pai from Academy in Pursuit of Engineering Excellence. Today we will continue our series on fluid mechanics. In that chapter 3 fluid kinematics, today we will discuss some of the examples in rotating and shear flows, and in those examples we will also include free and forced vortex. Now let us have a recap of what we have done in the previous videos. Okay. The first thing we had discussed is translation of a fluid element. Here, a fluid element translates when it moves from one position to the other without changing its dimensions. That is, its size remains same. Okay, and also it is not distorted. Okay, so if this happens, then it is a translation. Next, translation with linear deformation. When translation happens with linear deformation, here the velocity, which is given by V is equal to Ui plus Vj. Here u and small v are the velocity components in the x and y direction. The small u velocity component, which is the component in the x direction, is a function of x alone, and the component v, which is the component of velocity in the y direction, is a function of y alone. Only then there is linear deformation. And when linear deformation happens in fluid mechanics, it is always the deformation rate. Okay, so or the strain rate, linear strain rate. If we see the linear strain rate in the x direction, which is given by epsilon xx dot is equal to dou u by dou x, and the linear strain rate in the y direction, which is epsilon yy dot, is given as dou v by dou y. Okay, next we discussed what is rate of shear strain and rotation rate. When we see about this, here we have seen the rate of shear strain. Shear strain is about the rate at which the angular deformation happens. Okay, so in the figure which is shown here, d alpha and d beta is the angular deformation, and the total angular deformation is d alpha plus d beta. Okay, so whenever we take shear strain, it is the angular deformation which is happening there, and rate of that angular deformation we have derived in the last videos, that gamma dot xy or gamma xy dot, okay, is equal to dou v by dou x minus dou u by dou y. Now when we consider rotation rate, the rotation rate is the average of the deformation or average of the rotation which is happening. Like if you have a dash d dash is a line here which has moved from a dash a double dash by d alpha, and a dash b double dash has moved by d beta. When we consider rotation rate, it is the average of these two. That means now if you consider d alpha is in the anti-clockwise direction and d beta is in the clockwise direction. So d beta will be negative, d alpha will be positive, and when we take the average we get omega z, which is equal to half into dou v by dou x minus dou u by dou y. In the similar fashion we can derive this in the other two dimensions as well. So these are the three-dimensional shear strain rate in three different axes as well as three different planes. Shear strain in three different planes and rotation about three different axes. Okay, so now let us see how rotation rate and shear deformation rate will be there in polar coordinates, because polar coordinates is also important, or cylindrical polar coordinates we will see. Okay, so in the cylindrical coordinates system, it is r, theta and z. Okay, r is the radius, theta is the angle that radius moves, and z is the perpendicular direction to the plane of r theta. Now when we consider the strain rate gamma r theta dot here is given as dou v theta by dou theta plus 1 by r dou v r by dou theta minus v theta by r. Now this v theta by r, if you observe, v theta can be given as omega into r, and v theta by r, when we consider, it is nothing but omega. So this particular component here is nothing but the angular deform or the angular velocity. Okay, so that gets minus here in the case of strain rate. Similarly, in the rotation rate, it is half of those angles average. So here instead of plus, here it is minus, and instead of minus it is plus over here, and half of that because we are taking the average. So half of dou v theta by dou r minus 1 by r dou v r by dou theta plus v theta by r. This is the rotation rate. Now let us see in other dimensions. This is other two dimensions. This is how the strain rate and the rotation rate is there. Okay. Now if you observe, there is no component here of v theta. It is just direct. Okay. If you observe here, in the case of theta z, we see dou vz by dou theta. Okay. Now theta, you know, angle is without dimension, so r is multiplied by that. So it is dou vz by r dou theta. Rest everything is the same. So wherever plus is there, you have to put minus over here. Okay. So that is how we find out the rotation rate as well as rate of shear strain in cylindrical polar coordinates. These cylindrical polar coordinates will be helpful in pipe flows, vortex flows. Okay. So that is why I have taken this particular topic. Okay. Next, now we will consider some examples. Some of the examples, first example we will take is uniform flow in a shear channel, whether this is rotational or irrotational, shear or non-shear. Now the flow where the rotation is there, then it is called rotational flow. If it is not there, it is called irrotational flow. If shear is there, then it is called shear flow. Otherwise it is called non-shear flow or flow with no shear. Okay. So we will see that. First we will discuss a uniform flow in a channel. Now when you say uniform flow in a channel, here u, which is the velocity in the x direction. For example, if you consider here, if I consider velocity vector which is given by ui plus vj. Now this u is constant and u of xy, everywhere it is constant. Okay, that is a uniform flow in a channel examples, and v goes to 0. So since v goes to 0 here, sorry, here I will rub this off. Okay, so v goes to 0 over here. Okay, now let us see which coordinate system we have to use. We will use a Cartesian coordinate system, and in Cartesian coordinate system, this is the expressions for rotation rate and the shear strain rate. So the first column is about the shear strain rate and this one is the rotation rate. So now let us see what happens here. Since u is a constant, wherever dou u by dou y or dou u by anything, dou u by dou z or dou u by dou y is there, dou u by dou x, dou y, dou z, it goes to 0. And anyhow v is equal to 0, so the whole thing goes to 0. So my shear strain rate in all the directions is 0 and my rotational rate is also going to be equal to 0. So this is an example of a irrotational flow with no shear. Okay. Now next, let us consider flow in a pipe. Now when we consider flow in a pipe, we take cylindrical coordinate system here and we take velocity as a function of r, theta and z. Since the pipe is here, pipe is circular in cross section, we are showing the RZ plane here. Okay, Z is the direction of flow. Flow direction is this. Okay, so in this, the VZ component is a function of R. Okay, so here one of the main thing what happens is VZ is a function of R. Because VZ is a function of R and VR V theta is 0, we will see how the shear strain rate as well as the rotation rate is there. We will take the cylindrical coordinate systems, and here what is important is the Vz. Now Vz as a function of R has only some value. Other than that, everything goes to 0. That means wherever Vz is differentiated with R, only those components remain. So here there is no Vz, V theta, this is 0, this is gone, this is gone, this is gone. Okay, so that's why this whole thing goes to 0. Now Vz by V theta, no, there is nothing because Vz is not a function of theta, so it goes off. V theta by dou z gone, so this also goes off. Now what is important is this one, dou Vr by dou z is also going to 0. What is important is only this, so this goes off and what remains is only this. So at the end what we get is gamma Zr is equal to dou Vz by dou r. This is the component which remains. That means it has shear strain. Okay, it experiences strain rate. So it is a shear flow. Another one is the omega theta. That is, this omega theta remains. So dou Vz by dou r remains. Here one of the mistakes is minus 1 by 2 has to be there. Okay, so it is 1 by 2, minus 1 by 2 dou Vz by dou r. This is the rotation rate. So this is a flow where both rotation as well as shear is there. So rotation, here one of the things we have to understand, rotation does not mean that the whole fluid mass should be rotating. It means each fluid particle should rotate. Okay, here if we observe in this case, this particular particle which is there here in this case, okay, has moved in this fashion. So if I consider the derivation we had done in the last videos, we see the angle by which it moves here was called d alpha and the angle by which it moves here was d beta. Now if you observe here, d beta is positive here and d alpha is equal to 0 in this particular case. So what is d beta is equal to 0, only those things will come over here, and also it is positive. Now we have to understand here in this case, okay, it becomes dou Vz by dou z. This omega theta becomes positive because when you say dou Vz by dou r, if you see it is reducing as the r increases, z reduces. So this particular thing will be a positive quantity here. Okay, so omega theta will be a positive quantity because it is rotating in the anti-clockwise direction, and the omega theta will be half of d beta. Okay, half of d beta by dt. Okay, and in case of shear strain, it is d beta total. Okay, dou Vz by dou r, whatever the magnitude is there, that is the shear strain rate. Okay, so this is what happens in the flow in a pipe condition. Next we will see, so what is it? It's a rotating shear flow. Very important. It is a rotating shear flow. It may come in some of the theoretical questions. 1 mark question may come. A pipe flow is a rotating shearing flow, non-rotating non-shearing flow, rotating flow with no shear, non-rotating flow with shear. Like that, there are number of times in GATE exam or other competitive exams, there might be objective questions. So this will help you to answer that. Okay. Now let us discuss the free vortex flow. Now when we say free vortex flow is seen when there is a suction which is created, or maybe a sink where it is filled with water and somehow the plug which is stopping the water to flow is removed from the water. So what is going to happen is the flow which is there is going to rotate around a center, okay, where the sink hole is there, it is going inside. But when it rotates, the fluid particle, not the fluid particle, the fluid mass is rotating. I'll be very careful in I'm saying this, what I'm saying. It is the fluid mass which is rotating, or we can say the fluid is going in circular streamline. The streamlines is circular here, okay. But when we consider the fluid particle, okay, this can be observed if you throw a twig into a sink hole, or if you say there are a lot of times when there is a rainy season, we may see that because there is a drainage below and the water is draining into the drainage, you might see a whirlpool type of thing, a flow which is rotating flow you can see, or not. We should be very careful in saying, not saying it's a rotating flow which is moving in circular paths. Okay, so if you put a twig, you can see the angle of the twig does not change. The twig moves in the same fashion as we say here. If the twig is here like this, the next twig position would be here like this. This would be the twig position. Like this it would move, and there it is spiral in fact, but in the ideal case it can be considered as circular path. Okay, and here V theta, the tangential velocity. Here one of the main thing is that it will have only tangential velocity. So since it has only tangential velocity here, okay, so v theta is c by r, and here as the radius increases, the speed reduces. As the radius decreases, the speed increases. And yes, when it comes to the center, the velocity approaches infinity. Okay, so how those things happens, we will see in the later videos which I will be doing on vortex flows. Okay, and Vr is going to be equal to 0. Okay, now let us understand this. Now what is the coordinate system we have to put? The cylindrical coordinate system. Okay, and in the cylindrical coordinate system, this is what is given by gamma r theta dot and omega z, which we have discussed already. Similar way, omega theta z and omega r, as well as gamma zr dot and omega theta. Okay, now here what is important is wherever we have v theta as a function of r. So what is happening here? V theta is a function of r alone. So what is positive? Where dou v theta is differentiated with respect to, or v theta is differentiated with respect to only r. Okay, so where are the components? This is one component which remains. This is one component which remains. This goes off because Vr is equal to 0. This remains. This goes off. This remains. This is not there. This is not there because v theta is not a function of z. Correct. So this goes off. This goes off. This also goes off because Vr is 0, Vz is 0. So everything goes off. What remains is only dou v theta and this one. So only those things remains here. All the other things are gone. Okay. So what remains is those part, and we will see what is that. So now once we do that, what is happening here is v theta, wherever v theta is there, we will substitute c by r. Okay. So my gamma r theta dot is equal to dou by dou r c by r plus 0, and wherever v theta is there, we are substituting, wherever v theta is there, we are substituting c by r, so this becomes c by r square. So my gamma dot r theta would be equal to minus 2 c by r square. This implies that there is a, just a second students, okay, this implies that there is shear strain rate. So in this flow there is shear strain. Okay, whereas if we consider the rotation, now when we substitute these equations, we can observe that omega z goes to 0. Why? Because c by r is minus c by r square. When we do this, this is minus c by r square. This minus c by r squares and plus c by r square cancels to give omega z is a 0. So this free vortex flow is actually a irrotational flow. So the free vortex flow is a irrotational flow with shear. Very important. So it is a free vortex flow is a irrotational flow with shear. Very important to note how the position of this fluid particle is there, represented by the rectangles which are given here. By the rectangles you can see it doesn't rotate at all, but there is shear. Okay, why there is shear? We will see that. Why? The question, I'll come back to this slide later on and I will tell you why this shear is there. Okay, now let us see the forced vortex flow. Now when you say forced vortex is similar to the rigid body motion. The fluid particle is made to rotate by a help of, say, a cylinder which is rotated by a motor, such kind of thing. So it is similar to a disc being rotated. Okay, we have to understand this is the ideal case, okay, where it rotates just like a disc, and just like in this figure we can see that just like if you have a if you draw a figure, okay, if you draw a rectangle on a rigid body or a disc, metal disc, and if you rotate, how that rectangle rotates, similar way the fluid particle also rotates. Okay, so it goes in this fashion. Okay, now what is important here, when you rotate a disc, we see that the tangential velocity is a function of r, correct, and as r increases, the tangential velocity increases, and at the center the velocity is 0. The same thing is there in the forced vortex. where V theta is omega into r, where omega is the angular velocity and Vr is equal to 0. Now if you consider here, in this case we have to put the cylindrical coordinate systems, okay, and here in the cylindrical coordinate systems these are the strain rates as well as the rotation rates. Now what is important is V theta as a function of r. Anything else will go to 0. So since anything else will go to 0, what remains is this particular expression and this expression. So the similar expression in this one. All the other things goes to 0. Now let us see. Now if that is the case, we will substitute V theta is equal to omega r in this equation, and when V theta becomes omega r, then gamma dot r theta becomes dou omega r by dou r plus 0 minus omega r by r. Now if you observe here, in this case gamma dot r theta or gamma r theta dot becomes 0. That means shear strain rate in this case is equal to 0. There is no shear deformation of any fluid particle here, okay. Whereas if you consider the forced vortex, the rotation rate, we substitute dou omega r, wherever V theta is there, we will substitute the omega r, and since we substitute omega r here, we can see this becomes r goes off, so omega remains because it's a constant. Here r cancels, okay. So what is happening is this is plus omega, here omega, again omega plus omega is 2 omega by 2 is omega. So what is happening here? The rotation rate in this case is equal to omega z is omega, which is the angular velocity itself, okay. So now let us understand this further, okay. Now how is that when this is rotating in this side, we are not seeing the rotation about the axis, is it not? Are we seeing any rotation with respect to the axis of the fluid particle? Apparently we are not observing, but actually it is there. How it is there? Now if I consider this is the inside part of the fluid particle and this is the outside part of the fluid particle. See, when it is rotated by 90 degree, inside has come here, outside has come over here. When it goes by 180 degree, inside is here, outside is here. When it is going by 270, it's inside, outside, and again coming like this. So what is happening? You see this here. When you come from here to here, there is a 90 degree rotation. And when it is coming from this to this, there is a 180 degree rotation with respect to the fluid particle axis itself. So if I bring it this side, first initially it is like this. When it goes to 90 degree, it goes this way. And when it is 180 degree, it again comes to this fashion. And when it is 270, it is going to here. And then the other way around. So it is rotating, okay. So this is the rotational flow. Similar kind of thing is seen in gear trains, especially epicyclic gear trains. When you see epicyclic gear trains, there is a planet gears and the sun gear. If I say this is the sun gear and this is the planet gear, okay, and the planet gear is attached to the arm from the center, correct? So now the number of rotation this planet gear takes when it rotates one full rotation here while engaging with the sun gear is got by n plus 1, and this n is got by the ratio of teats between the sun gear and the planet gear. Then there is plus 1. Why this plus 1 there? The plus 1 is there because if in case it's not engaging and it is having a rigid body motion, that is arm as well as this planet gear is rotating, this arm is rotating, keeping rigidly this particular planet gear. That means planet gear is not rotating about its axis, okay, but still what is happening when it rotates one full rotation, it is having rotation of 2 pi, similar to what is happening in this case, okay. So forced vortex is a rotational flow with no shear, okay. Now when I consider the in the case of free vortex flow, what is happening? Shearing is happening. There is deformation because it has to deform so that it will counteract the rotation, okay. So when we consider, I have promised you the back side I'll come to the previous slide. Now if I consider here in the second case, which is free vortex flow, here if you observe, when it is coming from this position over here, from this position over here, when it comes back, what is happening? It had to rotate actually in this fashion. Okay, it has to become this. But the shear strain, okay, the strain rate is making it to come back to the same position. So shear strain rate is counteracting the rotation, okay, or it is opposing the rotation. So that is the reason there is no rotation, okay, in the free vortex flow. I hope students you have understood these things. If you have any doubts, kindly put that in the comment section, and you can always contact me. I have shared my Facebook page in the comment section. Kindly follow that, and in that Facebook page we have the number also, so you can directly contact me using that number which I have given in the Facebook page. You can contact me and ask for any doubts for that matter. Okay, so kindly subscribe my channel, press the bell icon for the further notifications. Generally my videos will be premiered, and when it is premiered I will be there chatting with you online. Okay, so you can make the full use of these opportunities, and best of luck for your exams. Thank you very much, students.